Just start?
Yeah, it's good.
All right, I guess it's past. Nice to see you again. Hope everyone's well. I'm not quite sure how long I'll go today, but not more than 2 hours. We can have a little break if you like, if that's a good thing. Is 2 hours kind of reasonable? Okay. So let me start by just giving you a little recap of where we were, right? So what am I trying to tell you about? I'm trying to tell you about some things in geometry, and I'm basically trying to tell you about the kinds of geometries that appear when you have supersymmetry. That's in some sense where I'm going. But there's a nice way of describing all of them using these Gstructures, and that actually allows you to describe some other things too. So we might as well do them all in one go, okay? So the key idea from last time was a Gstructure. And if you remember, the idea was, so we had some d-dimensional manifold M, and we have some group, which is a subgroup of the general structure group of the manifold, right? The GLD is how the tangent space of the manifold twists as you go around the manifold. That's encoding the topology. And we have the definition that, so a G-structure P, so P is a principal G subbundle P inside the frame bundle. So if you like, what it does is that it picks out a special set of frames, or special sets of frames, which transform into each other. So two general sets of frames, right? A frame is just a basis for the tangent space. Two general frames will be related to each other by some GLD transformation at each point. So for a G structure, you get a special set of frames which are related by G transformations. And so instead of getting all frames, we get a subset of frames that are related to each other by G transformations. And what this does in general is that it restricts the topology of M. So it basically says that the structure group, sorry, my handwriting is getting bad. The structure group, the tangent space, is G. So as I go around the manifold, the tangent is not twisting by as much as it could do. Right? Okay. So, does the basic idea make sense to people? Ask me a question if it doesn't. Or if it does, ask me a question. Okay? So, and then we had a whole lot of examples, and typically, you can define P by invariant tensors. So not always, but in many of the cases we're interested in. So, I'll just do that by some examples. So let's remind ourselves of some of the examples. So the most basic one, which is sort of one you already know, which is when the group is OD. And then what we can take, the sort of way it works is the way to think about these invariant tensors is to think about them in a couple of steps. So first of all, you think about some sort of standard form for the group. So what I mean by that is, consider in this case, you just take the identity matrix. Okay? And one way of defining the orthogonal group is as the set of matrices in GLD, right? We want to define it as a subgroup of GLD because that's the way we're doing it. So it's the set of matrices such that M delta M transpose is just delta, right? Or equivalently M transpose is 1. So that's what I mean by a standard form. We define the group as some subgroup of GLD that preserves something. And then we can have the invariant tensors. We can exchange between invariant tensors or frames. So we can, if we have a metric, GMN, we can require that the frame satisfies, when we contract in the frame, we get the standard tensor. So for you, you know that this just means the frames are orthonormal. So this is a way, if someone gave you a metric, it would be a way of getting a special set of frames. So that tells you that if I start with this invariant tensor, which is the metric, so that's the metric, then from that I can pick out special sets of frames. If I want to go the other way, I can define my metric in terms of the frames. And there I use the dual basis. Right? So now I'm thinking of a basis of the cotangent space. Sure. Do I just do this? Does that help?
Yeah.
Okay. So here I'm taking sections of the cotangent space. Okay, so I can think of it either way. I can either think of someone gives me a frame, and from the frame I construct an invariant tensor using this standard form. Or if someone gave me the invariant tensor, I can construct the frames by requiring it to look like the standard form. Okay? And then you could do this for other groups. So for, we looked at this for GLNC inside GL2NR. Then you can define the group. So we can define this as the set of matrices in GL2NR such that M, and I don't want to call this, I'll call it pi, M inverse is equal to pi, where here pi is minus 1, 1, minus 1, 1, minus 1, 1. So you can define the complex subgroup as the one that preserves this pi, and this is playing the role of, playing the role of I when you complexify. That's what's going on. We're thinking of complex things as pairs of real things, and that's what pi does. And then you can define the corresponding invariant tensors. So we can think of this as some E hat MA E A N times some, B, pi A B. And this is what's called the almost complex structure. Right? It has the property that I squared is minus 1. Or if we go the other way, so that's like the second one here, or if we go the other way, we can say that E, we define the frame by saying that E hat NA E B M times M N should be equal to pi B A, right? So that's the analog of this one. So I define the frame so that when I contract it into the invariant tensor, I get the standard form. Okay, does that make sense? Yeah.
Sorry. With the light,
yes.
now the reflection's making the right-hand side of the board.
So I shouldn't write there. Is that the best thing we should do? Should I turn it off for a moment? You can see what I wrote?
Now I can read it perfectly.
Okay. You guys tell me what I should do. Should I write in white? Is that better?
Previously, I think the boards were a bit more vertical.
A bit more?
I don't think the colour's going to change.
Colour's not going to make any difference? So I could do a couple of things. We could have the light on and I won't write past that line.
Yeah.
Does that, for the people over, does that work? This bit's all right?
Yeah, that's fine, yeah.
All right. Okay. I'll leave that and I'll try and remember not to go past that line. Shout at me if I go past the line. Okay, and then we did other examples, so I'll just write them down. So there was sort of the symplectic group inside GL2NR, and there the invariant tensor was some two-form. And it had to be non-degenerate, which meant that if you wedge it up n times, this better not be 0. And what else did we have? We had some SLDR inside GLDR, and that was a top form or a volume form, kappa, which was wedge n t star m. And this meant that the manifold had to be orientable. And then, just for good measure, there was the trivial case, so identity structure. So that's when the group just has a single element in it. And that means we have a unique global basis. So it picks out just one frame, right? Because any two frames have got to be related by an action of G, but there's only that entity. So there's just one frame that I have. And this corresponds to something being parallelizable. Right? It's a lot of structure on the manifold topologically to be able to choose D nowhere vanishing vector field, global nowhere vanishing vector fields. That's a strong condition. People ask me questions. Okay. And then, so I think I already said this, but P restricts the topology. And it allows us to decompose tensors into G representations. Right? So you can think of tensors on a manifold. For each GLD representation, you have a corresponding tensor. Right? And if I've got a G structure, what that allows me to do is to decompose those tensors, GLD tensors, into G representations. And in particular, let me just note, so in particular, so we always have, so for the Lie algebras, so if I think about tensors which are, if I write down here, can you see it? Yeah, okay. So if I would take Tm tensor T star m, right, that's something with one index up, one index down. That's actually the same as what I'll call the adjoint bundle for the frame. This is just, right, a matrix with one index up and one index down. I can just think of it as the Lie algebra for GLD. Right? GLD Lie algebra is just m by m matrices. Is that okay? This will also, that's just the adjoint, right, Lie algebra for the frame bundle. I'll just write it like that. And this will have in it, it will always have the adjoint for the P structure, right? When I decompose this representation, the GLD adjoint, because G is a subgroup of GLD, inside it, it will always have the adjoint of the subgroup. But then it'll have some other stuff. So all I want to stress to you is, like, just think about the way we did this. We defined our group in terms of these matrices M. These are like the group elements. They're matrices, M by N matrices. Here I can think of these things as like M by M matrices. Now instead of thinking of the group elements, let's think of them as the Lie algebra. Right? I'll just call that the adjoint bundle for the frame, right? The adjoint representation of the frame bundle. When I do this, it picks out a subset of matrices. In the Lie algebra, it picks out a subset of the subspace of the Lie algebra. So inside here, when I decompose into G reps, I'll certainly have the adjoint representation of G. I may also have other things. I will have other things. I'm seeing some frowns, so someone asked me a question.
Maybe just say that again.
Okay, so shall I say it in an example? Would that be more helpful?
Perhaps.
Okay, so let's just think about this thing, right? Let's think about OD. So if you do the Lie algebra, right, I want e to the x transpose to be the identity. So that tells me that x plus x transpose has to be 0. It tells me that x is minus x transpose. So it tells me that the generators of OD are the antisymmetric things. Let's think of x as being an element of Tm times T star m. If I do this point by point on the manifold, it's just a matrix, so I have something which has got one index up, one index down. Now, if I did in general, M is just a general M by N matrix, right? So if and the Lie algebra here, a general element of the GLD Lie algebra is just a general M by N matrix. No conditions. So if I take M by N matrices, that's like this, I can decompose them into symmetric and antisymmetric. The antisymmetric ones will live in the Lie algebra of OD. The symmetric ones will live outside. That's all I'm saying here. I take general matrices, and these would be the antisymmetric ones, and then the rest would be the symmetric. Did that help? So you can do that for each of these groups, right? So they'll always have a subset of these general matrices will be the ones that generate the Lie algebra. More questions?
So what is the symmetric algebra?
Well, it just generates the things in GLD that are not in OD. Right? Okay.
Can we make sure what the dots are? In other words, can we decompose the Tm,
Yep.
that T star m, into other representations of P and write it in this way?
Let's see if I understand the question. So I think, so this thing you can think of as a GLD representation because it's got one index up and one index down. So it's something like X, Mn. And all I'm saying is that since G is a subgroup of GLD, this representation will in general decompose into other representations of G.
Yes.
Yeah. But one of them will always be the adjoint of G.
So only, my question is
Sorry,
that we can only make sure that the adjoint representation will be there, but other representations.
But in case by case, these things will be different, yeah. Yeah. So the adjoint will always be there, but what appears here depends on what the group is and what the decomposition is, yeah. Yeah, good, sorry. Other questions? Okay. So that's where we were. So what I want to do now is so far these structures, we've said that they can constrain the topology. But in general, in physics, we're interested in typically in things satisfying differential equations, right? So we're going to I'm going to now think about further constraints you can put on the structure that comes from differential conditions. Okay, I'm going to put that there to remind myself. Okay, so what I want to talk about now is what's called the intrinsic torsion. Okay, so we're going to start with connections. So let me remind you about what a connection is. So I'm just going to consider completely general connections, right? So they're things that take, for the tangent space, they take things in the tangent space and they map to something which has a derivative direction and still has a tangent direction. So let's be really concrete. So if I take a vector, it maps into something which I call nabla n Vm, and this is just some partial plus some connection piece. I'm going to write it as gamma m p vp. So you know, everyone knows the example of the Christoffel connection or the Levi-Civita connection. These are the Christoffel symbols, but I'm doing it completely generally for the moment. Okay, so this is just some GL. So this is a GL NR connection. So I just have to specify these things. And they have certain transformation properties in order to be a connection. Everyone happy? Okay. So, and of course I can extend this to any tensor. So, for example, if I took the derivative of some tensor which had an up and a down index, this would be the derivative. And then on the up index, I'd act as on the vector index, and on the down index, I get a minus sign. Right. And etc. if I have more indices. Okay. And let me remind you of the other thing you can do, which is to define a notion of torsion. So we also have a notion of torsion. So the torsion tensor for a given connection is something which lives in it's got a vector index and a two-form index. And we define it as saying that if, so let's use the notation. So I'll use the notation that if I write nabla with v there, that just means I take a vector and I contract it into the nabla operator, right? So for the torsion, we define the torsion as a function of two vectors. So as a function of two vectors, it should be something which is, I contract the vectors in here, so it should be a vector. And I define it as the derivative along v of w minus the derivative along w of v, and then I subtract from that the Lie bracket. So if you remember, the Lie bracket is just Vm dm Wn minus Wm dm Vn. And remember, for any two vectors, this is still a vector. So concretely, you find that the tangent, this thing, mnp, is just lambda n mp minus gamma mnp minus gamma p mn. So it takes the gamma and anti-symmetrizes on the bottom two indices. So this is what we mean by the torsion. And we say just some nomenclature. So if the torsion equals 0, we say then the connection is torsion free. Okay. So you can do a bit more now. So now let's suppose we have, so let's given a G structure, P, we can now ask a bit more of the connection, right? So we can take a compatible, so suppose it was defined by some invariant tensors. There might be more than one of them, so some set of invariant tensors, psi I. So then we can define a compatible, so a compatible connection is one such that the derivative of all the invariant tensors vanishes. Okay, so that's a special class of connections such that when I take the derivatives of the invariant tensors, I get 0. Now, equivalently, if you know about principal bundles, or you can think of it as a connection on P. So we're used to thinking about connections as acting on tensors. If you know about principal bundles, you can also think of connections as just define them on the principal bundle themselves. Okay, but I'm not going to get into that. So equivalently, what does this mean? So equivalently, if I take a given frame, so equivalently, given a frame in P, right? So then if I take the derivative of the frame, well, let me write some indices just to be clear. M, N. This is in general some omega hat M B A E hat B N. Right? This is I'm taking the derivative of a vector, so I get back a vector. So I can always re-expand the answer in terms of the basis. That's what I've done, and this is just by definition the components of that re-expansion. Right? So, and we can think of this such that so if nabla is compatible, then you get this, and these guys have to live in things that act in the adjoint of P. So think about this, think of them as things in the Lie algebra. If this is going to be compatible with the structure, remember this tensor was invariant under G. So when I take the derivatives, I'm only allowed to do Lie algebra actions here that are in G, not in the whole thing. So long as this thing lives in the Lie algebra, i.e. this is a Lie algebra valued one form. Right, so it's like a one form because it's got an M, but this bit can only rotate in G because it's a compatible connection. That's the idea. Okay. So, or if we act on some vector expanded in this basis, then we can write the derivative of the vector using what we define above. This is just the derivative of the thing in the basis, and then here you pick up the action of this Lie algebra. Okay. So that just follows from what I defined above. So if you like, this is defining the connection in that particular basis. Yeah.
Just to be super clear.
Yeah.
You're taking the derivative in the direction of the M frame, right there.
So when I write M and M, they're just like coordinate directions. So I'm going in the coordinate direction M of the frame, and the frame is labeled by A. So I have D vectors here labeled by A. So for each one, when I take this, I'll get something that's got an M index and an N index. Now on the N index, I can do the expansion in the frame again. That's all I've done here. I've just expanded again in the frame. That's what defines these omega hats. Yeah. Is that good?
Yeah. Are there more terms, maybe in more general case? Because it's when we take derivative of E, or it's the only thing that could.
So this is the only thing that could appear, because this thing has to be a vector, and I have a basis, so I can always re-expand the vector in that basis. Yeah.
But what is then so special about this choice?
So these things completely general. That puts no constraint on the. Yeah, I should have stressed this. That puts no constraint on the connection. But if I require this thing to live in the Lie algebra of G rather than the Lie algebra of GLD, that puts a constraint on these things. So in the OD case, when I lower an index, this has to be anti-symmetric on the A and B. Yeah, that's the condition. The condition is that it lives in this ad P of the Lie algebra of G rather than the full frame, the full Lie algebra.
And would that enforce that the metric is, or the connection is compatible with the metric in that case?
In that case, it says the metric's compatible with the connection. Yes, the connection is compatible with the metric, exactly. Yeah, so I'm going to say that in a second. So one thing is, for any G structure, you can always find compatible connections. So compatible nabla always exists, right? And if I have given two compatible connections, right? There may be more than one. In general, there will be more than one. The difference between these two things is just going to be some tensor. It's just going to be some object that lives in T star M tensor ad P. Right? When I take the difference, I get rid of the derivative bit. So I just get something that's an honest tensor. Does that make sense? So if I have one compatible connection, I can get another one by shifting it by something that's in T star M tensor ad P. If I take one thing here which was anti-symmetric on A and B, if I add another bit that's anti-symmetric on A and B, it will still be compatible for the orthogonal case. Is that okay?
Sorry, I am a bit confused.
Good. I mean, not good that you're confused, but good that you asked the question.
So, if I want to define a compatible connection, I want this acting on some tensor to be 0.
Yes.
And this tensor must be defined on the J structure P.
Exactly.
And, is there any other restriction, like what this tensor should be?
No. So given a structure P, typically you can define it using a set, maybe more than one, but by defining, you can define it as there being a set of invariant tensors. So if it was an OD structure, the invariant tensor would be the metric. If it was, last time we talked about Kähler geometry, it would actually have two objects. It would have a symplectic form and an almost complex structure. But in general, there'd be some set of tensors. It might be more than one, but in many cases, it's just one. And those tensors define the G structure. You can either think of it as a subbundle, or you can think of it as defined by the tensors. So let's think of it as defined by the tensors, then a compatible connection is just one where the derivative of the tensors vanishes.
And if I just have this, if I only have one invariant tensor,
good, yep.
And then there I can still have
more than one connection.
Yeah.
Yes. Yeah.
So as long as the difference is the gamma blah blah thing still,
then they're still compatible. So let me do an example, and well, let me say what we're going to be. Let me give you what the key idea is going to be, and then we'll start doing some examples that hopefully will help. So here's the key idea. So the key definition. So we define a G structure P is torsion free if or integrable. Same thing. If there exists a torsion-free compatible connection. Okay? So in the space of compatible connections, is there one which has zero torsion? Or more than one? Is there at least one that has zero torsion? So just as a note, MB, mathematicians sometimes reserve this notion of integrable for something else, for something stronger. So you might see something where it says integrable, it means something stronger than this, but I'll use integrable and torsion-free as meaning the same thing.
Is this a related integrable to all the integrable stuff we see in other areas of physics?
Not sort of like integrable and having an infinite number of symmetries. It's, yeah, we'll see. It's more to do, yeah, I'll tell you what it is. Yeah. So it's not really the same. And this thing, you can't always do this. So if you have a G structure, you may not be able to always do this. And in fact, this is going to put differential conditions on the G structure for you to be able to do it. Okay? So let me do it by thinking about examples. And there's an example that you know and love, I think, which is the case of the metric. So let's do the example of an OD structure. So there we have a metric, right? So what do we want? We want a connection such that that is 0, and we need that the torsion is 0. Now you know there's a unique solution to that, which is the Levi-Civita connection. This has a unique solution. Which is the Levi-Civita connection. So that's where this thing looks like the derivative plus, and then here you get the Christoffel symbols. So I hope you've seen that, right? The way of defining Levi-Civita is it's the unique connection that leaves the metric invariant also has vanishing torsion. So just to be a little bit more explicit, so for this condition, right, what does that tell me? I need dm GNP minus, let me put a hat on that because it's the special one, it's the Christoffel. MQ QNGQP minus gamma MQPG and Q better be 0, right? That's the I'm just writing out that condition. So if you think about that, if I have two connections, so if I have two connections such that they both preserve the metric, then if I take the difference between them, acting on the metric Gn, right? I'm just going to get two terms like this. I'll get gamma prime and gamma. The partial derivatives will cancel, and I'll get something that looks like gamma prime minus gamma. I'll get minus gamma prime minus gamma MQN GQP minus gamma prime minus gamma MQPG NQ equals 0, right? If I call this thing, let's call this thing omega MQN, this thing just lowers the index, right? So I'll get omega M NP plus omega M PN. Am I doing this right? What did I do wrong? Sorry. Pn plus omega NP equals 0, right? Because this just lowers that index and calls it Pn. This lowers the first index and calls it NP. So you see that this thing has to be anti-symmetric on these guys. That's just what we said, right? It has to live in this thing, i.e. this thing is an element of T star M tends to the adjoint. So just requiring that the derivative of the metric vanishes doesn't determine the connection. I can shift it by anything that's anti-symmetric on the last two indices. Right? And then, but within that family, remember what the torsion is. The torsion's going to like say that the symmetric part has to vanish. So within that family, there'll be, it says that the anti-symmetric part has to vanish. Within that family, that will then pick out one thing. Yeah.
These are all local statements, like there's no manifold dependence?
Yeah, so this thing is a tensor, right? So I can think of it as each point on the manifold. It doesn't transform in any funny ways. Yeah. Yeah. So we saw two things. First of all, we could always find a torsion-free compatible connection. And secondly, it was unique. I don't know if I'm going too fast, too slow, too... Okay?
Wait, you said that it does not exist
in general.
But
For OD, thank you, yeah. For OD, we found it did exist. It always existed, whatever OD structure we took. Any metric, I can always find this thing. So it always existed, and it was unique. Okay. So what I want to do now is I want to do another example where it's neither always exists nor is it unique. And I'm going to go through it in detail so you can see what happens. And it's going to be the case of the complex manifolds. So before I move on, is everyone okay with the orthogonal case? Okay. All right, so
this means that it is torsion-free.
So every metric structure, every OD structure is torsion-free. Yeah. Okay. So now let's do the example of GL and C inside GL 2nR. So if you remember, we had the invariant tensor was this object I, this almost complex structure, right? Which had the property that it's squared to minus the identity. So what we need, a connection. So what we need is that the derivative of this thing is 0, and we also need that the torsion is 0. So let's see if we can find that. So we're going to have to do we need to do some decompositions into GL and C reps. That's what this calculation is going to depend on. So let me set up the way I'm going to do that. So first of all, I think we mentioned this last time, but you can decompose the the tangent space, the complexified tangent space, into 2 bits. And you can think of them, so if I have, and these are the eigenspaces under the action of I. So these are the eigenspaces for I. So what do I mean? So if I take I, so if V10 is in T10, then VIMP, V10P is just equal to I VM10. And I have to complexify because the eigenvalues are going to be plus and minus I because I squares to minus 1. So at each point I can find an eigenvalues like that. And similarly, if V01 is in T01, then IMP V01P is minus I V01M. Okay? Is that okay? And I'll use the notation, so I'm going to use a notation. So also, because the whole thing is real, we can think of V01 star is equal to V10. That's just some reality condition. And I'm going to use a notation. So if we take Vm, I'm going to write it as Vi v I bar, where this is the 1, 0 part and this is the 0, 1 part. So I'm going to sort of use an I index for things running in this space and an I bar index for things running in this space. So all this is I told you under a G structure you can decompose tensors, and under this structure vectors decompose into two different representations of this group. If I take a real vector here, it decomposes into an n component vector here and its complex conjugate. Is that okay? All I'm doing is, like, if I had v1, v2, v3, all the way up to v2n, then I just take things that look like v1 plus iv2, v3 plus iv4, etc. These would be the things in t10, and v1 minus iv2, v3 minus iv4, etc. Those would be the ones in t01. That's all I'm doing. Yeah?
Maybe just quite basic question. Can you just remind me why we're looking at the complexification of the tangent functions? Is that when they put a complex action on a real manifold?
So, okay, so it's just a little trick because the eigenvectors, the eigenvalues of this are going to be plus and minus I. In order to find the eigenspaces, I have to go into complex vectors. So that's the only reason why I'm putting a complex thing here. Okay, that's all. Okay, so now we've got some notation. So every index up or index down we can think of as having what's called a holomorphic index or an anti-holomorphic index. I can split it. So let's think about these conditions. So first of all, let's think about the torsion. So, oh, that is terrible. Okay. How are we doing? Okay, so let's think about the torsion. So the torsion lived in this space, which was vector and two forms. So I can think of the torsion as having M, N, P. So let's now decompose it under the way that I wrote it. So I can have components that look like T, I, J, K. That's where they're all holomorphic. I could have T, I, J, K bar. I could have T, I, J bar, K, but it's anti-symmetric on those two, so that's not going to give me anything new. I could have T, I, J bar, K bar. And then I could have T, I bar, J, K, T, I bar, J, K bar, and T, I bar, J bar, K bar. So I get 6 things. So if I decompose this representation into GL and C representations, that's all I'm doing, I would get 6 different things.
So just building on from that, we're looking at sections of the tangent bundle there,
Yep.
not the complexified bundle. So can you maybe...
Okay, so strictly speaking, I should complexify this in order to get these representations. Yeah. I'm being a bit loose with that. Okay. Or if you want, you can keep it, well, yeah, to a mathematician, you would have to complexify. Physicists tend to think of this being real and then saying that this bit's the complex conjugate of that bit. A mathematician wouldn't quite like that, but that's the way we're going to think about it. So here, if you like, I can think of T, I bar, J bar, K bar as being the complex conjugate of that guy, etc. Okay, so that's the torsion. So for the torsion, we get 6 things. So now we need to think about compatible connections. So what about, so now for the compatible connections, so we need, suppose we have two compatible connections. I said we could always find one. The question is, can we find, within the set of all connections, can we find one that's torsion free? So I can always write this thing as this one plus some omega. And remember we said that omega had to live in T star m tends to the adjoint of here. This is for GLNC, right? So what's the adjoint of GLNC? Well, if I take the adjoint bundle of Fm, that's the same as T star Tm times T star m. So if I have an element there, it's going to look like Rmn. And that I can split into Rij, Rij bar, Ri bar j, Ri bar j bar. And if you think about the adjoint has to keep us within this bundle or this bundle, right? If it's going to act in the group G, these are the eigenspaces, these are the invariant spaces, these are the representations. So the adjoint better keep us in those. So the adjoint acts in these bits. These are the adjoint. Of GL and C. If you imagine acting on this guy, it better keep you in the same space, because this is supposed to be a representation space. So it better just have ij indices. If it took a j index and made it into an I bar index, that would have moved it out of this space and put it in here. Okay? And what happens here is that this guy, the complex conjugate of that actually has to equal minus this one. It's just saying that the matrix is anti-Hermitian, but don't worry too much. Okay, so now let's see what the space of omegas is. So the space of omega, so we have omega MP, and what components can we have? Well, the T star index can be either I or I bar, right? The ad index have to be the same. So what we're allowed, we could have omega I j k. We could have omega I j bar k bar. We could have omega I bar jk. We could have omega I bar j bar k bar. Those are the four possibilities, right? Has to live in the adjoint, so these are either jk or j bar k bar. And then this index could be either I or I bar. I'm enjoying the noise. Does this make sense? Okay. So if we work out, so the torsion of nabla prime is going to MP is going to equal the torsion of nabla MNP plus, and then it's just going to look like omega NMP minus omega P N, right? That's by definition, that was what the torsion was. So when we shift the connection by omega, we can shift the torsion by this much. So let's call this the change in the torsion. So let's see what things we can get for the change in the torsion. Well, we got to anti-symmetrize on these indices. So we can have something where it's I, j, k, where they're all unbarred. That's fine. We could have something where we've got one barred upstairs and a barred and an unbarred downstairs. So that's I bar, j, k bar. We can have something where there's a I upstairs and a barred and an unbarred downstairs. And we can have something where it's all barred. So I'm just trying to keep track of the representations. So if I shift the compatible connection, I can shift the torsion by things in these 4 representations. Right? So what I need to do is I need to take those 4 representations and compare them to the general torsion. So that one's there. This one's there. This one's there, and this one's there. But these middle 2 are not there. So it's just linear algebra. By choosing omega, shifting by omega, I can get rid of all these 4 parts of the torsion, but I can't get rid of those 2 parts of the torsion. So in general, I won't be able to find a torsion-free compatible connection, right? Because in general, there'll be some of this torsion and I won't be able to get rid of it. So by shifting nabla, we can remove all the torsion except the components T, I, J bar, K bar, and T, I bar, J, K. And these bits are what we call the intrinsic torsion. And these things are independent of the choice of connection. So it wouldn't matter which connection you chose, the connection would always have to have these bits of the torsion, because we can't change them, right? So they're somehow intrinsic to the structure. Okay, so for GLNC, there exists a torsion-free structure only if these components vanish. Right. And this is actually the complex conjugate of this one, right? These are so. Okay, so this is an example, unlike the metric. For the metric, we could always find a torsion-free connection. So the structure was always torsion-free. for this almost complex structure case, you have to put some conditions. So let's try and understand those conditions a little bit more. Well, first, does anyone have any questions? Okay, let's try and understand these conditions a bit more. So let's rephrase. So let's consider V and W that are both going to be holomorphic objects. Okay. If I take the derivative of Vn, this is going to look like dm Vi plus omega m ij Vj e hat I m, right? Because it's compatible, it can only act in the adjoint. So this thing, this is going to be an element of T star m times T10. It stays in T10, right? When I take the derivative of this thing, because it's a compatible connection, it keeps me in that representation. It's still in T10. Is that okay? That's a property of compatible connections. When you take derivatives in some G representation, they stay in that G representation because the connection's compatible. It can't rotate it into something outside that representation. Okay, so let's think about the following. So if we work out if we think about the remember we have by definition that nabla VW minus nabla WV minus the bracket was equal to the torsion. So in particular, this tells me if I look at the component of this that's in this, so if I look at the component in T01, this bit can't contribute because I just told you that the derivatives keep you in 1, 0 because it's a compatible connection. So this will be 0, and this thing will, so this must equal T I bar nabla mn vm vn wm with, I guess, a minus sign. And if I remember, these are really in the T10, so this is actually just I bar j k vj wk. So if I take the Lie bracket of two things in T10 and I look at the component in T01, because I have a compatible connection, that's actually just going to be the torsion of that connection, but with exactly this I bar jk components. That's exactly what appeared here. So if the intrinsic torsion vanishes, so the intrinsic torsion vanishes is the same as saying that if I take the bracket between these two things, it still lives in T10. So another way of defining the torsion-free structure is that if I take two vectors, two holomorphic vectors, and I take their Lie bracket, it should still be holomorphic. That's the same condition. If you've ever seen complex manifolds, this is the way it's usually defined. Okay. So just to complete the story, you can define a projection. So we can think of V10M as being delta Mn minus I times I Mn acting on some general vector that will project. So that's a projection from TCM into T10. And if you work out this, this is like an involutivity condition. Right? If I take two things, it stays in the same space. So this involutivity is equivalent to saying that something called the Nyhan-House tensor vanishes. So there's a tensor which is N, M, P, Q. So you just use these projections in this statement, and you get the following. Let's see if I can get it right. M, R, D, P, I, R, Q minus DQ, I, R, P minus V, L, P, dr, MQ minus dr, Q, dr, MP. This thing has to be 0. So again, that might be what you've seen before. And it also allows you, what it means is you can introduce so we can introduce complex coordinates so that if I have a V10, I can write it as some VI d by dzi and V10. And if I have a V01, I can write it as some VI bar d by dz bar I bar. So having a almost complex structure, the GLNC structure, is not enough to introduce complex coordinates. But if the intrinsic torsion vanishes, or equivalently it's involutive, or equivalently the Nyhan-House tensor vanishes, then you can introduce complex coordinates. So you can think of having complex coordinates on your manifold. Do you want to take a little break? So hopefully you have the idea of the looking at torsion-free structures. And in this case, it gave us what are called complex structures. Not almost complex structures, that's if you just had the G structure. If it's torsion-free, then it's an honest complex structure. This field is full of like weird names for things, right? Almost appears all over the place. So if something is not torsion-free, it's often called almost. And then sometimes it's called nearly if it's got something else, or like almost nearly, or like, yeah.
Actually, what's the G and G structure?
What is the
G and G structure?
I think it's just the group G. But I don't know. That's what I always thought. And just to say here, the connection, the torsion-free connection, is not unique. So on a complex manifold, on a metric manifold, there's a natural torsion-free connection, which is Levi-Civita. On a complex manifold, there's no natural connection. And you'll sometimes see people write down, so if you have a little bit more structure, you can define different things. There's something called the bismuth connection. There's something called, what are the other ones? Chern connection, Levi-Civita connection, and so on. People define different connections as being interesting ones, but there's no natural one just from the complex structure. All right, so what's the general picture? So let's do the let's do the general. So let me draw the general picture. And then we'll do a couple more cases, and then we'll try and get some payoff, which is how we think about supersymmetric backgrounds. So in general, so recall that in general, we're going to have some omega, which is the difference between two connections. So given compatible lambda and lambda prime, this thing is going to be a section of T star M tensor add P, right? That was the point, because it's compatible. Instead of being the whole of GLD, you just get it in the parts that act in the group. And then if we take, if we define tau of omega to be the difference between these two torsions, then we get a map so tau you can think of as a map that takes sections in here and maps the intersections of Tm wedge 2 T star M, because remember that's where the torsions live. So that was exactly that map I did, right? I wrote out what this looked like for the complex case, and then we worked out what components we got under this map. And then you get the following picture. So here's the space of connections, or well, here's the space Tm plus wedge 2 T star M. So that's the space of torsions, or tau. I'm going to draw a line here, which is the image of tau. So as you take this map, this is the 0 point. So as you take this map, you can move in this direction. So that was what we saw. As I change this guy, I can move along here. And so in general, I'll get, if I have some T naught, I might have two connections here and here. This is the 0. So in general, I can shift them by something. This would be shifting by some amount tau. But I can't, in general, shift it down to 0. There may be some bits I can move along this line by changing my connection, but I can't move in this direction. So you can think of this bit as being the intrinsic torsion. And it's the part that I can't change, right? If the intrinsic torsion vanished, then I could always shift so that I get a 0 torsion. But if this bit doesn't vanish, I'm stuck on some line up here. So I can think of the intrinsic torsion as being an element really of this thing quotiented by the image of the map, right? Under the image of the map, I could move in this direction. If I had a metric on this space, I could choose this to be in the orthogonal direction, but I don't always have a metric on this space, so I have to just think of it as quotiented by this thing. Does that make sense? And so we have a torsion free, and this depends only on the structure. So it's some intrinsic measure of the structure. And for a torsion-free, so for a torsion-free structure, so we need that this intrinsic torsion is 0 for a torsion-free G structure. And in general, this map may have a kernel. And the kernel of the map tells me if if tau has a kernel, if the kernel of tau is non-zero, then the torsion-free connection is not unique. Right? Because there'd be two different connections which had the same torsion. Okay. So let me just run through a couple more cases to tell you what happens when you want the torsion-free condition. Okay? So for the complex one, we saw that it was this vanishing of the Ninehouse tensor. So let's do a couple more. So for SLDR, right, the invariant tensor was this kappa. And you can always, this is always torsion-free. Like the metric case. You don't have to do anything. Any SLDR structure will be torsion-free. More interestingly is if we did the symplectic case. Remember there we had this two form. And then torsion-free corresponds to saying that the form is closed. And you get an honest symplectic manifold. Ooh. So a symplectic manifold is one that has a symplectic form, a closed symplectic form on it. Right? So again, we're getting natural conditions, right? By asking for torsion-free, we get symplectic, which is good. Asking for torsion-free for the GLNC gave us complex, which was good. If we did UN, so both these cases it's not unique. So nabla not unique. And here again, nabla's not unique. If we did UN structure, that has two things for it, right? So we needed the almost complex structure and the thing that looks symplectic, those two things together. And the torsion-free corresponds to the Ninehouse tensor vanishes and d omega equals 0. So it's separately complex and symplectic. And this is what's called a Kähler manifold. So if you have a torsion-free UN structure, that's a Kähler manifold. What if we did an identity structure? Right, then we have some preferred frame. And we would have a connection, so compatible connection. We would require that this thing was 0.
Sorry, could you please be a little bit more explicit? Like, only if my basis has this UN structure, I will end up with a Kähler manifold, or as long as along the any boundaries on that I get a UN structure, then I still have a.
So a UN structure, you can think of it as in two ways. Either as the existence of these two things on the manifold, both nowhere vanishing, or as a special set of frames which transform under UN. Those two statements are the same. So rather than thinking of them in the frame, I'm going to think of them as defined by these invariant tensors. And then if they satisfy these differential conditions, then I have a Kähler manifold. So a Kähler manifold is something where you have both these things and they satisfy these differential conditions. I'm not sure if that was quite your question.
So like, my question is that I have a, because if I want to define a manifold, then I would have something like leaving the tangent bundle or something leaving arbitrary bundle. So my question is that this UN structure is a restriction only for the tangent bundle or for the...
It's a restriction on the tangent bundle, so it means the tangent bundle twists just by UN. But given the tangent bundle, that actually tells you how every other tensor bundle twists. So if the tangent bundle just twists by UN, then every other tensor bundle will also only twist by UN.
Is the inverse also true? Like if I have a bundle that I don't know if it's on tangent bundle or not.
No, so there it could be more restricted. So it's a special property of the tangent bundle that if you know the twisting of the tangent bundle, then you know everything. Yeah. For example, if I just took functions, they twist. That's a very special tensor. They don't have any twisting at all. But that doesn't tell me that there's no twisting of the tangent space. Yeah, I understand. Are there any other questions? Okay, so in the identity structure we have this, and we have, for a compatible connection, we would need that. This actually, this actually defines a unique connection. Just compatibility. I've just forgotten the name of it. It will come back to me. And if we, just by thinking about the bracket, the Lie bracket between any of these two things, just as we did before, this is just going to be given by the torsion of this connection. So if it's torsion free, this better be 0. If it's torsion free. So you see that actually the frame all has to commute. So for a torsion-free identity structure, you get a fixed global frame and they all commute. That tells you that actually locally you can introduce coordinates such that the frame is just given by d by dxa. And so the manifold is actually just Rn, Rd, quotiented. It could be quotiented by some discrete group. So for example, M could just be the d-dimensional torus. Could be flat space, could be a torus quotiented by something, could be one direction flat space, the rest a torus, and so on. But basically it's flat space. Okay, let's do G2. So for G2, we had this special 3 form, right, that defined the structure. And what happens is for it to be torsion free, this has to be closed and co-closed. So let's say a little bit about that. So this is the Hodge star. I hope everyone's familiar with the Hodge star. To define the Hodge star, you need a metric, right? You have to raise and lower indices. So how can I, but here I've just got a G2 structure. So however, since G2 is a subgroup of O7, is a subgroup of GL7, phi defines a metric. And so I can use that metric to teach the Hodge dual. So this was a 3 form, this thing will be a 4 form. Is that okay? Let me tell you how you do that. Do you want me to tell you how you get the metric?
Yes.
Okay. So what you do is you do the following. So you define something which has a pair of indices and then 7 indices. So, and I define this in the following way. So I just take phi m, p1, p2, phi p3, p4, p5, phi p6, p7, n. So this is something which is symmetric in 2 downstairs indices, and it looks like a top form in the other ones. Okay?
So G is not the metric that you get if you were just dealing with an O7 structure?
So it's not yet a metric. It looks like a weighted metric. It's weighted by some top form. So I'm trying to construct the metric here from phi. I'm trying to give you a constructive way of getting the metric. Now what I can do is I can just take the determinant of this thing on the mn indices. Right? If you think what that's going to be a section of something that looks like the determinant bundle. Right, the determinant bundle is just if you take the determinant of something, right? So the determinant bundle is the same as the top form bundle. It's totally anti-symmetrized. So because the determinant of a metric is going to transform like the determinant bundle squared, but then each component's going to have a weight with it, so that's going to transform like the determinant bundle to the 7th power, because it's got this thing's like the determinant bundle. This has got 7 components, so I get the determinant bundle to the 7th power. So this whole thing looks like a dissection of the determinant bundle to the 9th power. So I can get rid of this weighted part by just and hence define the actual metric as this funny weighted metric divided by the determinant of this thing to the 1/9. Yeah.
Probably misunderstanding something, but why
It's okay.
would it not make sense to use the, so if G2 is a subgroup of O7,
Yep.
can you not use the metric that you would get from the O7?
You can. So there is indeed a metric here, which would be GMN, and that's what this is. However, you might ask, what's the relationship? Since this is there, this must be determined by phi, right? So I'm just showing you explicitly how it's determined by phi. That's all I did. Yeah, you're absolutely right. Because someone asked me to. Okay. And again here, I should have said with the Kähler case, so again here the nabla is unique. Okay, so let's just make one more comment. So generally, if G is a subgroup of OD inside GLDR, right? Then P defines a metric, G, because of this. And we know, and if nabla is compatible with P, then nabla of G must be 0, right? Because if it's compatible with P, it's acting in the algebra which is inside OD, and that means it must also preserve G. So this tells you that the torsion-free connection must be Levi-Civita. Right? Because there's only one torsion-free connection which is compatible with G. So if P is torsion-free, then the torsion-free connection is just a Levi-Civita one and is unique. So if you have a G structure that's a subgroup of the orthogonal group, then checking for torsion freeness is the same as asking whether the Levi-Civita connection preserves the structure. If the Levi-Civita preserves the structure, then it's torsion free. Okay. All right, so now I was going to move on to, yes?
What do you do when you define G in terms of G tilde? What are you doing with the other 7 indices on G tilde?
Okay, so because I was sneaky, right? So if you have something with 7 indices, right? It's really just a choice of a function, if you like. I mean, not a function, but it's just there's only one degree of freedom in this. So what I really mean is take G tilde mn 1, 2, 3, 7. Take that one, and then take the determinant. Yeah. Good. Any other questions? Okay, so let's talk about supersymmetric backgrounds in the last 15 minutes.
Is the G that people typically work with generally part of like a subgroup of an OD?
So for the supersymmetric backgrounds, it always will be. But you'll find other places in physics where sometimes you're interested in things that are not that. So symplectic is the obvious thing. Complex, those things are not of that type. Okay, so the idea is we get interesting geometries from supersymmetry. So if you like, a lot of the geometries that mathematicians are interested in, from a physics point of view, are just supersymmetric things. That's a sort of nice general kind of principle. So we're going to think about some compactification. So we got some manifold, and we're going to think about some Minkowski space. Let's keep it simple to start with. And then some internal space, d-dimensional space. And we'll take d plus n to be 10 or 11. So we're going to either be in sort of 10-dimensional supergravity or 11-dimensional supergravity. And if you remember, we had So we're going to think about what are called supersymmetric backgrounds. So we want a supersymmetric background. So that corresponds to, in the supergravity, we need that there exists some parameters, epsilon, that preserve the supersymmetry transformations such that the variations vanish. Right? So we want to be able to find, we have a background and we want there to be some supersymmetry variation to the background such that there's no variation. Okay? So if you remember, and these are going to be bosonic backgrounds. Right, if we want to put a lot of particles in something, we want to have a coherent background, it better be built out of bosonic things, right? Out of fermionic things, you have Pauli exclusion, so it's not going to, you're not going to have nice coherent backgrounds. So if you remember, so since they're bosonic, we have that the variation of the fermions is going to look like the bosons. Sorry, the variation of the bosons is going to look like the fermions. So that's going to be 0 automatically because there's no fermions in the background. And if we do the variation of the fermions, well, what did they look like? So they look like we had the variation of some gravitinos. So this was in general in M theory or type 2. They look like some Levi-Civita connection on the spinor plus something that depended on the flux acting on the spinor with some Clifford algebra action. And this was for type 2 or M theory. And then there was sometimes some extra dilatini which looked something like gamma n plus something involving the flux. And that they appeared in type 2. Okay? So I wrote down those variations, I think, on the last time. So all I want to say is that what appears here is the nice Levi-Civita connection, the thing you're familiar with. But there's some other terms that depend on the flux. So what are we going to do? So let's just, to keep things simple, we're just going to think about turning off the flux. So let's set the flux to 0. And let's decompose the spinor. So we can decompose it under the Clifford algebra n1 times the Clifford algebra d. So this is sort of on the Minkowski space. This is on the internal space. Or if you like, this is spin n minus 1, 1 times spin d. So I'm going to take those epsilon spinors and I'm going to decompose them into spinors on the non-compact part of the space and spinors on the internal part of the space. So in general, I can think of that then as I've got a spinor here and it's going to split into 2 bits, chi tensor eta. So I'm telling you it in general structure. Of course, in detail, you have to work out what these spin groups are and so on, right? But don't worry. So this is the bit on R n minus 1, 1. This is the bit on M. And all we've got is the Levi-Civita. Now, the Levi-Civita on the flat space is trivial. It's just d mu, right? So the bits we have to, and that just tells you that this spinor has to be constant. Okay, so if I set the flux to 0, this tells me that we're interested in just having the Levi-Civita on the spinner is 0. That's what we need to solve, right? In order to have a supersymmetric background. Because this bit's 0, this variation is going to have to be 0. Just tells us this is 0. If that's 0, this is 0. Just contracting with a gamma matrix. So on M, we need to solve that the derivative of the internal spinner is 0. That's the condition we need to solve. This is called the killing spinner equation. So if we can find a spinner on the internal space that satisfies that condition, then we'll have a supersymmetric background. If we can find 2, then we'll have 2 lots of supersymmetry. We can find 3 lots, and so on. So what it's saying is, if you can find a spinner satisfying that, then the theory in flat space will have some number of supersymmetries depending on how many solutions you have. Am I being clear, or maybe not? Someone asked me a question.
So will there be a set number of ones for each?
So yeah, so depending on how much supersymmetry you want, you might ask for 1 solution, 2 solutions, and so on.
So you tune that?
You tune that. That's your choice. And it's going to put more and more structure on the manifold the more you require. Yeah, good. Okay, so here's the payoff. This is just, but this is just a torsion-free G structure. Okay. So if you think about your structure as being defined by the metric plus the spinner, right? We have Levi-Civita is torsion-free, and the condition that Levi-Civita of G is 0 and Levi-Civita of eta is 0 just as it's compatible. So I'm being slightly sneaky. I'm thinking now of the structure as defined not by tensors, but by a tensor and a spinner. I'll come back to that in a second, right? But just bear with me. So what this should be is a G structure where G is the subgroup of spin D such that G acting on eta is just eta for all G in the group, i.e. this is just the stabilizer group of eta. Right, if you think about what is the invariant thing, right? What group preserves, so these are supposed to be invariant tensors. This is invariant under OD. So the question is, what's the subgroup of OD, or better, spin D, that leaves the spinner invariant? That's going to be our structure group. That's going to be our G structure. Okay? Yeah.
What happens if you don't have vanishing fluxes?
That's a super good question, and hopefully I'll tell you in the next lecture. I'll tell you a little bit about some simple cases and then try and ask the general thing. Okay, but you get the idea, right? We have these two things. They're preserved by the Levi-Civita. So Levi-Civita is compatible. It's also torsion-free. So let me do an example, and then I'll write a table, and then I'll stop. So let's do an example. So suppose we take spin 6. So we're on D equals 6. Now, you may or may not remember that spin 6 is the same as SU4. And the spinner just transforms in the 4-dimensional representation of SU4. So if I have some fixed spinner, let's write it as epsilon 1, 0, 0, 0. Let's write it as alpha 0, 0, 0, right? You see that the stabilizer group of epsilon is equal to what? Well, the part of SU4 that just rotates down here. So the stabilizer group will be SU3. So the G structure for the pair G eta is SU3, which lives inside. Okay. So if I have a supersymmetric compactification on a 6-dimensional space that preserves one spinner, I have to have a torsion-free SU3 structure. That's the same as Calabi-Yau. So I'll go through these examples probably next time. Okay? If it was, well, no, let's stop there. Let me write the table, and then pizza's coming, and then we can stop. So we can do some basic examples. Essentially all the ones you'd be interested in. So here's the dimension of D. Here's the number of killing spinners. Right, so the number of solutions. And here's the group. So you just go through and you just do a little bit of group theory, which is to work out what the spin group is, and if I had 1, 2, or 3 independent solutions, what the stabilizer group is. So if it's in 4 dimensions, and I just have one killing spinner, then the group is SU2, which is the same as SP1. If you know that notation, that's the sort of symplectic group defined using the quaternions. If I'm in 6 dimensions, and I have a single spinner, it's SU3. So what do we call the manifold? Sorry. This is Calabi-Yau 2. This is Calabi-Yau 3. This counts the complex dimension of the space. If we're in 7 dimensions and I have a single spinner, it turns out the stabilizer group is G2. This is a Joyce manifold. If I'm in 8 dimensions, if I have 1, it gets a group spin 7. If I have 2, it gives a group SU4. And if I have 3, it gives a group SP2, which is the same as USP4. I don't know if you know those groups, but anyway. This is sometimes called a Cayley manifold. This is a Calabi-Yau 4, and this is what's called a hyperkähler manifold. Okay? So supersymmetry in each of these numbers of dimensions gives you some torsion-free G structure, and these are the Gs. Okay. I guess we should stop. So next time, I'll tell you a bit more about what these structures are, and then we'll start turning on the fluxes and see what happens. All right. Any last questions? Yeah?
So if there can have invariant objects of any kind, is there a G structure with an invariant spin 3.5 particle?
So a G structure with invariant symmetry class particle. Yeah, in principle, you can just go through, I mean, it's just some representation theory, right? You just have a given representation and you ask there to have a singlet in that representation. Yep. So you can do whatever you want. I mean, for the ones connected to supersymmetry, you look at stabilizers of spinors, but yeah, you can certainly do all sorts of other things. Yep. Any other? Yeah.
So when you were writing your Killing spinor equations, you factorized your Killing spinor into
Internal extent. Yep.
And these are the solutions you find when you do this factorization. If you didn't do that factorization, what would change?
So if I did it on the whole 10-dimensional space or 11-dimensional space, so there I would be interested in just G's which are subgroups of 9-1 or 10-1. You get more interesting things because of the signature, but you can certainly do it, yep. So some of them will look like this, but you can also get other things. Yep. Yeah.
If I had several Killing spinors, is there a notion of R symmetry in this that would rotate them into each other?
Exactly. So yeah, so the R symmetry in the theory on the non-compact space is exactly rotates the different Killing spinors into each other.
Okay.
Yep. So if I do, yeah, so you know, if I compactify this, well, yeah. Yeah, let me leave it at that. So yeah, if I have here, they would rotate these things into each other. Yep.
But just within the compactification, there's nothing to say about that, really?
Not at this level. When we start talking about anti-de Sitter backgrounds, it gets more interesting. Yeah. Any other questions? Okay, let's stop there. I'll let you have your pizza.